Any questions? Questions? Yes?
Yeah. So I didn't really understand how to calculate my current grade from the statistic.
I can't. The way the grade formula works is it takes into account your grades on the exams, the exam is the final. I don't know what your final grade is going to be. The homeworks, which first we have to get all the homeworks in, and then the sum of them gets curved. I mean, I use the same, a similar curve. So you could guess what my curve would be.
Okay, so what is mean grade given so far?
What's that?
What is mean grade or average grade?
I haven't.
No, not on this class.
Oh, in general?
Yeah.
Oh, how many people live in class? 12. I'd be generally I'd like to give 4 or 5 A's, 3 or 4 or 5 B's, however it turns out. And then if someone does something that just doesn't rise to a B, then they get C's or D's. But that's typically how it pans out. And looking at what's been happening so far, I would imagine that's how it's going to pan out here again. I mean, there have been some, and you know who you are, who've done very good work, and there's been some who know who you are who haven't. The numbers are just more or less like they always are. So the only time when I was alarmed was with that first exam, but I guess it worked better the second time around.
After homework 3.
Huh?
After homework 3 is completed, you can get homework.
Aha! Practice actually does work, huh? All right, so having heard that, now I'm regretting. So in homework 4, if you remember, originally I said, we'll be coming back to the CPS computation because it'll be assigned as a homework. But it actually was yet another one of those fairly complicated homeworks. And so I decided, in the interest of moving forward, not to put it in. Maybe now I should, would give you more practice. But so it's not there. If you want extra work, I'll gladly give it to you. So forget everything I said about going back to that CPS computation, that more detailed, refined algorithm. We're not going to do. Homework 4 is on. It's the quiz app, web app, and Racket is actually, once you get your head around it, it is ridiculously easy. When I did it, I said, gosh, this is actually a good way of doing web applications. And so I'm having you do it in Rails so that you can see that in Rails it actually is not as satisfying. Which is why I'm giving more points for the Rails solution than for the Racket solution. It's harder. It's harder in Rails. So the Racket people are onto something. If they could just get their performance up to speed, that would be a much better way of doing these kinds of applications. Problem 3 builds on today's labs, easy. Problem 4 again drives home this point that continuations might actually be useful for something. Because it makes another kind of things that is tedious to do really simple. All right, so today I want to go through this kind of more practical thing on, let's say you actually want to do something useful with continuations, and let's say you're using Scala. How can you make sense out of this reset shift stuff that at the beginning does seem rather opaque and abstract? So the general structure that we've looked at for a reset and shift looks like this. We have a reset block that delimits the continuation. That means that when the continuation is called, it can never go up beyond this point. Whereas when we call the continuation inside scheme, it went back all the way to the REPL. So that was an undelimited continuation that just captures the entire rest of the computation. So the traditional sense of computation is of continuation is the rest of the computation. And here it's not quite the rest, it's up to this point.
So, how much is continuation actually in the scheme? The continuation actually didn't go and end at REPL. It kind of printed
just keeps on going.
Okay, so it doesn't end that.
Well, it never ends. It just keeps on going until the very end of whatever it is. And that, in this case, that means the thing that you typed into the reference. So when you call the continuation, it just jumps to the original point and just keeps going on forever for the entire rest of the function. Whereas here, when you call k, it doesn't go on forever. It translates whatever is in between the reset into CPS, and whatever is in here means some kind of a computation, and that is the function that's being captured. So it will not go on until the very end. So, so when you run the reset, it executes the before, of course, and then as soon as it finds the shift, then it'll do the inside, and then it'll exit with the last line of the inside. And that's always true. Whenever you hit a shift, then that means that you execute the inside, and then you get out. So when you call the continuation, then it rewrites everything in here. So you have this big thing, the shift becomes the hole that gets punched out. Then that means the rest is a function. It's the function, lambda something, and then this thing here. That's the function that gets called. Now it's possible that when you run the continuation, that you might again run into the shift. Even though the shift looks like it was punched out here, but if you have a loop, you might run into it again. And in that case, then you again get outside of the continuation. And so that's the basic mechanics. And now the question is, how do you design with this? The rules seem kind of bewildering. You've gone through the lab, you kind of have a basic understanding of what the flow is, but then let's say we want to solve a problem with continuations. How do you deal with that? And that's what these slides are supposed to do. So what reset shift gives you are a basic framework for jumping in and out of a loop. When we wanted to do that in Scheme, we had to use two sets of continuations, one for jumping in, one for jumping out. And so the reset shift kind of gives you one set already for free. So anytime that you have a structure where you want to repeatedly doing something, delivering results, coming back, delivering more results, coming back, then the reset shift actually gives you a perfectly good structure. So rule number one is figure out where you want to return the results to, and you put the reset in there. So that might be, if we say define an iterator, the iterator needs to return results. And so you would put the reset into the iterator. Inside the reset, you put the loop control. You will want to loop over something. You will want to iterate over something. And you can use while loops. You can use recursion. But you unfortunately cannot use things like map. Why not? Because they're not CPS. Everything that's inside the loop is rewritten into CPS style, and the system does not know how to rewrite those things into CPS. This sounds like something, that would be an interesting research potentially to do that. It's got to be possible to do some of it, but right now the state of the art is that they figure these continuations are meant to be building blocks, basic building blocks for some library writer. And if the library writer is a little bit inconvenienced, that's okay. It's not the end of the world. So these would be buried deep inside some library code that someone writes. The normal user should never have to see this. And I'll come in a minute to why a normal user might actually. All right, so so we put our control logic inside here using a while, using a recursive function, and of course anything can be expressed in that way. As the very last expression, we want to put in the value to deliver when the loop has finished. And so that's also a good thing to keep in mind. You remember from the previous homework that the last case was kind of tedious, and your head hurt when you figured out exactly what would happen when you were at the end of, say, that sequence of zeros. So here the rule is actually very simple, that the last thing inside the reset is what you want to deliver when the recursion is finished. And then there is this point where you want to jump back into, and that's where the shift goes. So wherever it is that after you have a result, that result gets returned, and then you want to jump back into frame, and exactly where that happens to shift. Inside the shift, you need, of course, capture the continuation so that you have it available from the outside, and you compute the value that should be delivered. So those are the basic rules. So let's see how they work in a practical example. So we'll have a tree walk, and for whatever reason, I now use a slightly different data structure for the trees. So this is kind of like we had in the very first Ruby example many months ago. A tree is made up of leaves, and the leaves can hold values, and of nodes. The nodes themselves do not hold values. So a tree it's an n-ary tree. And so you have values in them. We have a generic visit method that looks exactly like the one that we had in Ruby. That we have a visitor function here. And I'm not sure we've seen this the Scala code, so I briefly have to walk you through this. So T is a node. Notice that we have two different subclasses of tree, leaf, and node. And so this, if I draw a UML diagram, so I have tree, node. So this expresses the idea that a tree can either be a leaf or a node, where a node is a non-empty tree and a leaf is an empty tree. Not like a tree with one thing in it. And so we'll consider both of them as trees. Yes? Yes, I'll come to that in just a minute. So notice that the tree class itself is abstract. So we say a tree is either a leaf or a node. It's kind of similar to the way we say that a list is either an empty list or a non-empty list. And so now the only thing that we need to worry is what does this case classes mean? They're used in pattern mapping. So if we did this in an object-oriented way, we would now use inheritance and dynamic dispatch to figure out how to deal with these structures. But in a functional language, one often deals with these finite variations where there's only a couple of cases by using pattern matching. So over here we say T, and we'll make a match on whether it's a leaf or a node. So you can think of this as an instance of match. And yes, an instance of match is frowned upon in object-oriented programming because it makes the system non-extensible. But in the case where you build these data structures, how many kinds of trees are you going to have? They're either leaves or they're not leaves. There's never going to be the third case. So in these cases, it's considered just fine to do this, this instance matching. Now notice over here we're saying a leaf, and a leaf contains a value inside, and we want that value, we want to be able to extract that value by matching on leaf of V. Then if I have, say, a leaf of 5, then V is automatically bound to 5. This pattern matching only works when you declare this class as case classes. Otherwise, you cannot extract the values that are inside it. So the case class is necessary to make the pattern matching stuff work. Technically, what happens is when you declare a class as a case class, then it makes a method where one can extract each of the fields out of it. It makes a set of methods for this. And the match case kind of construct calls those methods behind the scenes. So we'll just have to take this on faith. It has nothing to do with continuation. I'm just giving you this code. Over here we want to have the nodes, the node sequence, and this looks a little technical here. It's some sequence of children, and because this is a var args thing, and var args work a little bizarre in every language, you have to use this syntax. Just trust me, this binds t's to the sequence of children. Now over here, I'm now iteratively walking through this list of children. It's a little funny. I actually use a bar here so that I can walk through this because the for each, the more obvious construct, that's one. What do I do? For each child, I visit the ith child with the same visitor. So if I have a leaf, I apply the visitor. If I have a non-leaf, I recursively apply the visitor to each of the children. So that's my classic visitation. Same objection as always when you have a tree. When you visit it, you get to call this method here, 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 here. What if you only want the first one? You can't do it with a visitor visits all of them. So what I want is an iterator in this case, and so I want to have a way of turning the visitor into an iterator. And I'll use continuation. We've done this before, and now the only question is how can we do it in Scala? And so what I want to show is that if you follow these rules, it's actually pretty easy. So we have to design this iterator. Here the iterator is a function that consumes a tree, and then it returns a function. The function that it returns has no parameters, and it returns, this is apparently a tree of integers. Right? So when I say, I have my tree, and now I make an iterator of that t. Then I can call I, that calls gets me the first value back, and call I again, that gets me the second value back. All right. So it's a function. Now I have to write that function. The function takes no parameters, and it returns some stuff. So there's a special case at the very beginning where I wanted to start the iteration, and I recognize that beginning by saying the very first time I have not yet captured the continuation. So I'll set a variable here to null, and I say the very first time I haven't yet captured it, and that's just my simple little way of detecting that I'm doing it for the first time. That's actually kind of a dangerous thing. I have to make sure to reset this thing to no, but you'll do that anyway. And so somewhere deep inside here, I'm putting it inside the same function here, but maybe it's actually called inside some other function. Somewhere deep inside here, there must be a shift. In that shift, I capture the continuation. So the very first time the iterator does its thing, starts the iteration. Eventually, there'll be a shift that captures the continuation. If it's not the first time, then I can simply invoke the continuation and I get back to wherever that shift is. We'll see in a minute where that ends up. So that's how you do the first versus later thing. The only caveat is that this resetting here, you have to make sure that that happens every time that you request the iteration. So we want to mark the point to which we want to return the result with a reset. So where do we want to return the results? We had this point previously in the previous slide, in the iterator, where I have this function. So I want the results to pop out of this thing, so I should put my reset around it. So here it goes. Now I put my control flow inside the reset. What's my control flow? It's the visit recursive function. I could put in a loop or I can put in a recursive function. So here's my visitation. And so here's my tree. And it takes two things. It takes the tree and the function that should be applied everywhere. And I'm putting the shift inside that function. This looks maybe a little bit confusing, but remember, visit is a functional way of visiting a tree. It takes a function that gets applied to each loop. And so in that function, the shift will be called. So you can think of this thing as a loop for each node in the tree. then where do we want to jump back in? Well, as it turns out, this is very simple. Every time that we have visited a leaf, that's where we also want to return to, and that's exactly where this function is being called. So this is the visitor for the leaves. It's a function. It gets called at each leaf, and that's where we want to get back into the phrase. So we surround everything inside there with a shift. So inside just the shift, we capture the continuation. We've already seen that. And then we'll return the value that we want to return. In this case, it's particularly trivial because this visit thing, which you can think of this for loop over trees, hands this function the value that is being visited, and that's just the value that I want to return. I want to do nothing else. So when you put it all together, this is what it looks like. So the iterator takes a tree, it returns a function that gives it a new integer each time. That function takes no parameter, and when it's called the very first time, it enters this reset here, does the visitation inside here. This is where I want to get back to every time I deliver the result. Now this is a good idea to check that typing thing that we talked about before to make sure that all the typing is consistent. So if you remember, there were these three types, A, B, and C, and so there were the thing that you feed into the continuation, and that's the type of the shift. And what do you feed into the continuation? You give it nothing, because when we call the continuation, we're not calling it with anything. We're just saying jump back there. We're not saying jump back there with this particular value. So that's where the unit comes in. And then there is a type that gets returned in the shift whenever we happen to run into a shift, versus in the reset when we have to pop out of the reset. And so in this case, they're both integers. So over here, we're returning the actual value that's in the leaf. Over here, we're returning the 0 that indicates the end of the iteration. They're both integers. So in this case, we don't really need to know these values because, well, do we need to know the values?
Yes.
Why?
Using the types.
Yeah, why do we, yes, that's right, the types. Why do we need to know these A, B, and C types? Yeah, when we declare, the reason we need those pesky things, we had to put those @CPS annotations whenever we declared a function. But there is no function here. We didn't actually need any functions to write this. Yeah, it's all in one place. Nice and easy. Almost. There's one function. Which function? That's a good question, whether we would have to annotate the function that we're passing to the visit. And the answer to that is kind of yes. But really the function that there is visit. Visit is our function, right? And so we need to just write visit so that it works correctly. But as you'll see in a minute, you were also right, because that other function is also, we need to worry about. So we need to write visit. And so when you write visit, you need to figure out how to annotate visit. Now visit takes a parameter, this visitor function, and we also need to annotate that. And so that's where you need to know what is visitor. So the rule was that if we had we needed to annotate with what? It was at CPS param, I believe B comma C. But if B and C were the same, we could use at CPS B. So here we can annotate with CPS int, and here are those annotations. So now this thing says, so visit is a thing that will be rewritten as a CPS returning an int. And in the process, it also calls another function, the visitor function, and that itself is a function that is rewritten as a CPS int function. So what does the rewriting mean? That means that when visitor is actually kind of easy to understand. Visitor right now takes a single parameter. When it is rewritten, it will take the continuation, that other parameter that tells it what to do with the result. So visitor right now consumes an integer and then produces nothing. So the CPS rewrite will, what exactly will it do? Will it eat the integer? I don't know. I have to look at it. So the rewrite will get a second function that now will. I guess it should consume the unit, right? So I'm not sure why. I have to think about it. But the after is it does get a second function that tells us how the future is going to look like. And we're going to see those functions. They'll look baffling, but we'll kind of see the outline of them, and it'll be plausible that someone could have figured this stuff out. All right, so those are the annotations. So, when a little bit more on how this rewrite really does work with the reset shift. So we have what we saw before. Reset is a parameterized function with no arguments. It's a yes, parameterized function, and it consumes this function here. Now the shift, why does it use map? This map here is not the regular map. They just call it map. You'll see the map appear, but what it means is that this after is going to be rewritten in CPS, and then it needs to know the continuation, and that's going to be this transform here. I think we're just going to have to look at the example. I can't understand it anymore either. So here's the transform iterator. Yeah, so the dummy does us no good. So now let's try to.
Is this something in the compiler?
Yes. Yes, so the compiler will take what we have written and turn it into straight old code, because remember, the Java Virtual Machine has no support for continuations, so it needs to rewrite it into regular old code. So, unfortunately, this one here by itself is not very helpful, but we need to see how visit is transformed. Yeah. Wait to show me. So the while here is translated into a loop. So we're going to be coming into this with a tree, and let's say the tree doesn't have, has a node here right now. And so we're going to begin, at the beginning I is going to be 0. Now we're going to be recursively calling visit, and it's going to say that after you've done that, be sure to increment I by 1. And it has to put that computation in here so that it's sure to be done. The dummy unit argument is a little odd. It's because everything has to have an argument. We need to be in general, we need to be prepared to carry values from one step to the next. But here we don't, and so we're having a value of type unit, you would like to think that's a function with no arguments, but everything is typed to have an argument of some type t, and that type t here is the type unit, and one has to give the parameter some name. So I call it something. So this just says, after you're done, make sure to increment I by 1. And over here it says that after you're done, make sure to call the loop again. And then the loop gets called again. So, so to summarize, why do we care about continuations? Before doing that, let me walk through this one example in the homework, which is why I put it up. So in the homework, you're going to be looking at a GUI application that has a login button, and so after the user clicks on login, some dialog pops up. This username, you know, the typical dialog, password, and there's an OK button. And then if everything is OK, then your process continues in the normal way. Otherwise, you need to somehow repeat this thing. And so actually this happened to a group of students I was working with last year. We were doing a cell phone application that had to work both on Android and on BlackBerry, gruesomely enough. And we had exactly this problem, that the login had this dialog. It could fail, and if it failed, one had to return to the dialog. And if it succeeded, there was a second step that also had to be executed, and that step could also fail. And so when you write this just on Android, you can kind of do it. You have to have an event handler for all of this, and then the event handler has to kind of keep track of which part of success or failure you are, and then when it gets called again, it strings itself one thing further. When we wanted to do this in a portable way so that it worked on both of them, it became very, very unpleasant. And the project manager was very surprised because he said, this is simple. It says, if it succeeds, you do this, and if it fails, you do this, and if it fails again, you do that. It's just an if-else else. Why are you guys having so much trouble with it? And so we had to explain to him that, well, these dialogues, they run on the event handling thread. On the event handling thread, you can only do a itty little bitty thing, and then you have to return to the main application. So it was not an option to wait on the event handling thread until we got the answer back from the server, because we would have frozen the UI in that situation. So we were in the situation that we had to make a call to the server, and we had to essentially tell the server to say, and when that call returns, then do this. And when that call returns, then do this. We have to independently reinvent continuation passing style. So that's exactly what continuation passing style is. It says, and when you figure out the answer, then do this. And so we ended up rewriting the very simple while and if thing that we got from the project manager in CPS. Not knowing that that's what we were doing at that time, but when we looked at it, I said, oh, we just rewritten it in CPS. And it was tedious. It was very fragile, it was very error prone. But that's what one has to do for a lot of these applications. What you can do, as you'll see in the homework, is you'll be able to write this in Java with in Scala with a way that you can actually write a while loop like this. You can write it inside a while loop, because with the continuations, you can just jump back into the while loop. And the way you will achieve that is you'll be using shift and reset under the hood in a way that the application programmer does not see. And so that's kind of what continuations are meant to be there, that you can produce effects such as do a loop where each fragment of the loop is done on a separate thread, such as the event handling thread, and so that it's short-lived and it doesn't block the thread. You can program these abstractions so that the end user can blissfully use them. So this is something that actually, as it happens, Microsoft had invented just around the same time. In C# 5, they have an await statement that does exactly the same thing. So if you look at what it does, is it rewrites some undergoing stuff in CPS style, and that way you can say, well, I want to wait for this, and then when the event finally happens, then that part is being called as a continuation. The trouble with the Microsoft approach is it only works for this one syntax that they dreamt up with. It doesn't work for anything else. So the Scala syntax is completely general, and you can do other control constructs. Await is probably the most useful one, but there may well be others that we've not thought about. No. I mean, it'll then store the continuation. It's just like how it worked with Racket, where the continuation is just stored somewhere, and when the thing finally happens, then the continuation is being called. And if you have a real continuation like in Racket, this is kind of a piece of cake. But when in this case, the continuations are being constructed by the CPS rewrite process by the compiler. And so it's much harder to understand what goes on. So the general point for continuation is you want to say, get me back to this place later. And that is just an awfully useful situation that we want to have sometimes. And so the two things that are like the biggest selling points for continuation is if we want to turn a recursion into an iteration. That's like for these 3 visits that we beat to death. And the other one is for user interface events, where one has to wait a long time for the answer to come. It's really beneficial to be able to say, let someone else deal with this event, and when it finally comes, let me get back to this point. So those are the two poster child features of when this thing makes sense. There are 2 ways on how they can be implemented. One is by copying a part of the runtime stack, or really the runtime method invocation data structure, which is really, I shouldn't say stack, because if it's a stack, then it's hard to do. And the other one is by manually transforming the code. We've seen both of these. And so it's not something that the end user programmer will ever see. It's meant for people, the 1% of wizards who produce stuff that the other 99% can use. So if you're out there demonstrating, saying, I'm the 99%, then continuations aren't for you. But if you, for the 1% of people who provide these features for the others, and sadly are not as richly rewarded as those other 1%, then continuations are just a ticket. So it's the most advanced control structure that anyone has dreamt up with. So, all right, so let's do this lab. And so in the lab, I want you to follow the design recipe in the multiply list elements thing. I know it's a boring thing, but it shows the design recipe very nicely. And then I want you to look at the transform that comes out of it and see if this is such a simple case where the transform is somewhat comprehensible. All right, let's do that, and then we'll look at it together and wrap it up.